Let's take a look at problem 11.2. In this problem here, we have two 15mm steel plates with a yield strength given to us as 400 MPa. These are butt welded using an E70 series welding rod. So this is going to be important when we look up our properties here. And good welding practice, which is going to go into our assumptions. So the wording here is important as far as our assumptions we make. The weld has a length of 90 millimeters. And that they're asking us to find is the maximum tensile load that can be applied to the joint safely with a safety factor of 3. So they give us our SF of 3 there. They also give us this diagram here, 11.2. So we can see here are the two steel plates, 15 millimeters thick, two forces going out this way, and here's our butt weld right there. So we know the weld length, 90 millimeters. We have our yield strength of 400 MPa, our safety factor of 3, and we know it's an E70 series weld. So we've had a chance to read through the problem statement and look at the given schematic. The next step we want to do is write out our solution to the problem. On the first page being the same as before, we want to write down everything that they give us, simplify down the given diagram, figure out what they're asking us to solve for, and to make any assumptions that we can from the problem statement before we start a solution. So the first thing that we do is we take a look at that problem statement and everything they give us and write down what we know. So we're given the fact that there's two plates. We know the thickness of these plates is 15 millimeters, so we can write that down here, that our thickness is equal to 15 millimeters. And we know that it also tells us in the problem statement that our yield strength is 400 MPa. Now it tells us we're using E70 series welding rod. So that's going to be important when we go through and figure out a couple of properties for that from our book. And we'll reference back to section 11.4 for that. It tells us that our weld width is 90 millimeters and we have a safety factor equal to 3. Now the thing to think about here is these are in millimeters. We may need to convert these to meters when we go through and solve for a final solution. So they want us to find the max tensile load that can be applied to the joint safely with a safety factor of 3. So we know, again, we have a safety factor of 3 here. And from the problem statement as well, we can go through and figure out that we have a weld efficiency of 100%. And that's given, if we go back to our problem statement, it tells us that it's good welding practice. So with that good welding practice, we're assuming a weld efficiency of 100%. So now we want to go through and begin our solution. And where we want to start for our solution is with section 11.4, where we're taking a look at the specified yield strengths for E70. So now we want to take a look at section 11.4 from our textbook. And this is on page 334. This is for welded joints subjected to static, axial, and direct shear loading. There's a lot of good information in these first 3 paragraphs here that you should read through, but what we want to concentrate is take a look down at the 4th paragraph here. So in the 4th paragraph it says that welding electrode material strength and ductility specifications have been standardized by the American Welding Society, AWS, and the American Society for Testing Materials, ASTM. So we've heard of both of those societies before. Now for us specifically, for example, welding electrodes that we're looking at in our problem here in the E60 and E70 series, where we're looking at the E70 series, are designated E60XX and E70XX. Now, the 60 and the 70 indicates tensile strengths of at least 60 or 70 KSI, respectively. So we're looking at tensile strength here of 70 KSI. Now, the last 2 digits indicate the welding process details, not necessary for our specific problem right now. Specified yield strength for E60 and E70 series. So now we're looking at yield strength. So this is what we need to actually come up with, are about 12 KSI below the tensile strengths. So we want to subtract 12 KSI from our 70 KSI of the tensile strength for our E70 series. So for the next step in our solution, we go back to our assumption where we assumed 100% efficiency based off of a problem statement. And now we want to find our max tensile load that can be applied with a safety factor of 3. So recall this relationship here for our safety factor. The safety factor is equal to our yield strength here times our area over the force, where we're looking for force. So what we want to do is rearrange and solve for F. So F is equal to our SYS times A all over our safety factor here, where our A can be found by the dimensions given in the problem statement. We have the thickness and the length. So we convert from millimeters to meters. So this is 0.015 meters times 0.09 meters. Instead of 15 millimeters and 90 millimeters, we now convert to meters here. So we have an area based off of those dimensions there. We have a safety factor of 3, and we found our value for our yield strength here, 399.6 MPa. We can plug that in. We end up with force is equal to 399.6 times 10 to the 6, because we want to convert to pascals and not megapascals. So our units work out are 0.015 meters, 0.09 meters divided by 3, which when we plug this in, we end up with a force, which is our max tensile load that can be applied of 179.8 kilonewtons. Now let's take a look at problem 11.3. So in this problem here, we have two different steel plates with the yield strengths given to us as 50 KSI. These are attached by 3/8 inch parallel load fillet welds. So it tells us the weld thickness and tells us parallel load fillet welds. These are shown down below in this figure here. It's an E60 series welding rod, so we can go back and use that information there to look up the properties about the welding rods. And good practice, good welding practice. So again, that's going to give us some information as well for our assumptions. Each of the welds, it gives us a length of 3 inches long, and it tells us a safety factor is 3. Now they want us to find the maximum tensile load that can be applied based upon that safety factor. So now we can take a look down here. Here's our given schematic. You can see the loads right over here. Here's your weld length of 3 inches. It's an E60 series welding rod that's used. Yield strength is given to us as 50 KSI for the plates. H is equal to 0.375 or a 3/8 inch. Safety factor is equal to 3. And we'll note here there are 2 of these 3-inch welds. So that's going to be important as well as we're solving this problem. Now we've had a chance to look through the problem statement, the next thing we're going to do is organize this in the correct format. So we want to figure out, what do they give us? What are they asking us to solve for? What assumptions do we make? And from there, we want to figure out a plan for how we're going to move forward and what key equations we should use. So for example, 11.3 here, what do they give us in the problem statement? Well, they tell us that we're using E60 series welding rods. They give us an H value of 0.375 inches, which is the height of welds. They give us a yield strength of 50 KSI, and they give us a safety factor of 3. And then we redraw out our schematic over here. Okay, we can see we have our weld length over here, 3 inches as well, given in the schematic diagram. We have our forces out here. We have our 2 different plates. And what do they want us to solve for? Well, they're asking us to solve for the max tensile load that can be applied here to stay within our given safety factor. So from this and the wording of our problem, we can make 2 assumptions. One, throat length is given by T equals to 0.707 H. Now, the next page here, we're going to go through and how we come up with this assumption, where this comes from. Where this is going to look at is back at figure 11.7 on page 335. So assumption 1, we're going to go through a whole derivation on where this comes from and how we can get this from this figure. The second assumption we're going to make is that the weld efficiency is 100%. So from our assumption, we determined that we needed to go take a look at figure 11.7. So shown here is 11.7. What we want to look at is part A up here on the right hand side. So this is the type of weld that we have going on for our specific problem. So if we zoom in at a 2D cross section of the two plates in the weld here, we can see up in the top right, we have this geometry going on, where you have the height going up this plate as h, the length going over here is h as well, and then you have our hypotenuse here that'll have some known value, and then thickness you can see is this diagonal length here, the max thickness of this weld. And this is given to us in the chart as t is equal to 0.707 h. So reference to h being the height and length of this weld here. So what we're going to do now is break this down and go through a little bit of the math behind how we come up with this value for t relative to h. So taking the information from figure 11.7a in our textbook, what we want to do now is break down the geometry behind what they give us in the diagram and figure out how they come up with our relationship between t and h. So this is a simplified version of the diagram for figure 11.7a. We have a right triangle here. We know height of h, length of h here. Then you have this hypotenuse over here of c. And then t is this max distance here, right up the center from our bottom point down here to the center of c over here. So we want to figure out how does t relate to h. So there's a couple different ways to do this. The way that I'm going to go through here is going to go through Pythagorean's theorem. So we say a squared plus b squared is equal to c squared. So in our case here, there's your a, b, and c, or h, and c. So we do this out here, h squared plus h squared equals c squared. Rearrange it. H squared plus h squared becomes 2h squared is equal to c. Then I'm going to divide both sides by my 2. So if I divide both sides by 2 here, I end up with h squared is equal to c squared over 2. So now we're going to do the same thing for just a portion of this. So if we want to do with t here, what I'm going to do is take a look at, let's just take a look at this right triangle over here. So if I take a look just at this right triangle over here, c becomes c over 2 for this length between there and there. Then I have my t and my h. So we have a right triangle with my hypotenuse now as h and my sides as t and c over 2. So I redraw that out over here. Here's my right triangle. Here's c over 2. Here's t. Here's h. So if I use Pythagorean's theorem here, I can say that t squared plus c over 2 squared is equal to h squared. So that's what I have. T squared plus this over here is c over 2 squared is equal to h squared. Now I want to go through and solve this for t. So I rearrange it a little bit, move this back over the other side. So t squared is equal to h squared minus my c over 2 squared. So I take a look at this here and say, okay, I'm going to square this out to take into account the fact that this is in parentheses here. So now I have that t squared is equal to h squared minus c squared over 4. So I'm going to pull out a 1/2 here so that I have a c squared over 2. So I pull that out front and I have t squared is equal to h squared minus 1/2 times c squared over 2. And the reason I want to do that is because my c squared over 2, I have a relationship from my Pythagorean theorem from the entire triangle up here. So c squared over 2 is equal to h squared. So I can replace this with an h squared, which does exactly what I want to do and eliminates c to get it in terms of h. Because if we recall, we want the formula in terms of t and h, not in c. So all of this is to eliminate c from this here. So I plug in my h squared for my c squared over 2 here. I end up with t squared is equal to h squared minus 1/2 h squared. So h squared minus half h squared, we leave here. Now I'm going to take the square root of both sides. So t squared is equal to the square root of h squared minus 1/2 h squared. So h squared minus 1/2 h squared is simply 1/2 h squared. So t is equal to the square root of 1/2 h squared. Separated out, t is equal to the square root of 1/2 times h with the square root, this is 1/2 there. Square root of 1/2 is equal to, t is equal to 0.707. Move the paper up so you can see that there. So again, we said t is equal to the square root of 1/2 h squared. So this then breaks down to t is equal to the square root of 1/2 times h. So we can break that down again. The square root of 1/2 is 0.707. So t is equal to 0.707 h, was exactly what we were given in our assumption and where we pulled this from figure 11.7a. So now that we have an expression here for T, which we just derived from figure 11.7a. The next thing we want to do is use that information to calculate our throat area. The throat area is going to be this value for T times the length of the welds. Now the thing to think about here is we have two welds, one on each side of that, so it would be 2 times L. So we multiply this length for both the welds times our T value here in order to get our throat area. So we're in this problem here, we have a value for H given in our problem statement, and we have a value for L given in our problem statement as well. So we can plug in these numeric values here. We know that given to us, H is 0.375 inches, and the length, again, is 3 inches, but there's 2 welds, so don't forget that 2 when we go through and calculate the throat area. So we plug this back into our throat area equation here. We have our T value times our length. So we plug this in, 0.707 times 0.375 inches for H value, times our length here, times 2 for both of the welds of 3 inches. Calculate this out, and we end up with a throat area is equal to 1.59 inches squared. So now that we have this here, the next step is to go through and calculate our yield strength, and we're going to go back to section 11.4 in our textbook in order to come up with this relationship here. So now we head back to section 11.4 in our textbook. This is welded joints subjected to static, axial, and direct shear loading. What we want to do is concentrate down here on the 4th paragraph. So in the 4th paragraph, what we have here is that a welding electrode material strength and ductility specifications have been standardized by the American Welding Society, AWS, and the American Society for Testing Materials, ASTM. So for us, we have a little example here that welding electrodes in the E60 and E70 series, where we're interested in E60 for our particular problem here, are designated as E60XX and E70XX, where the 60 and the 70 are going to indicate the tensile strength of at least 60 or 70 KSI. So what that's telling us for our problem is for E60 that the tensile strength is going to be a minimum of 60 KSI for our problem there. So that gives us that information. The last 2 digits indicate the welding process details, which we don't have to worry about. The next part that we are concerned here is for the yield strength. So specified yield strengths for E60 and E70 rods are about 12 KSI below the tensile strength. So for ours here, it's going to be 60, which is the tensile strength for E60, minus 12. So that's where we're going to get our yield strength from, is from this relationship here of 60 minus 12 KSI. So that brings us back to this relationship here. So now we've just seen from section 11.4 in the textbook here, we can get our yield strength to equal that tensile strength minus our 12 KSI for the E60 rod. So this gives us an SY of 48 KSI. So the next step after that is to take a look at our distortion energy theory. So this comes from figure 6.10 on pages 177 to 179 of our textbook. So now we can go back in our book to chapter 6 and take a look at figure 610. And again, this goes between pages 177 and 179 for this section in our textbook for distortion energy theory. So this is our plot for distortion energy theory. And what we want to pay attention to is the distortion energy theory predicts that the shear yield strength is the square root of 3 over 3, or 0.577 times the tensile yield strength. So this is the information we're going to use in the equation we're going to use in order to write down our shear yield strength for our problem. So taking that information from figure 6.10 back on pages 177 to 179 of our textbook for distortion energy theory, we now can calculate that our shear yield strength is given by this relationship of the square root of 3 over 3 times the tensile yield strength. So this ratio of square root of 3 over 3 becomes approximately 0.58. So SSY is equal to 0.58 times our SY to get our shear yield strength from our tensile yield strength. So plug this back in for our particular problem here, where we already calculated our S sub Y earlier in this problem is 48 KSI. So we can plug this in here, and now our shear yield strength is equal to 0.58 times SY is 48 KSI. So our shear yield strength is equal to 27.8 KSI. From there, now we can go through and calculate our tensile load. So we have this relationship here that our force here is equal to our SYS, or our shear yield strength, times our area divided by our safety factor. Now for our problem here, we've just calculated that our shear yield strength is 27.8 KSI. Our area, we've calculated earlier, is 1.59 inches squared, which is our throat area here that we can plug in. So plug in our known values. F is equal to, when we take KSI and put it in terms of PSI, 27,800 times our 1.59 divided by 3. Pay attention to our unit analysis for this, and we do end up with pounds in the end of 14,700 pounds for our tensile load.